Welcome, everyone. I am pleased to introduce the overview for the upcoming Go 1.26 release, arriving in February 2026. This version heralds the era of automated modernization, representing a transformative shift in our development workflow. We are moving beyond the constraints of manual refactoring toward a paradigm of intent-based code evolution. Over the next few minutes, we will explore how these new capabilities will allow us to modernize our code bases more efficiently and effectively than ever before. The satisfying developer experience is rooted in the powerful synergy between language features and tooling architecture. As we anticipate the arrival of Go 1.26 in February 2026, we are moving beyond simple syntax updates. This release marks a transition toward automated evolution, where the language and the toolchain work in concert to manage complexity. On one hand, we have expressive language enhancements, such as built-in iterators and the new expression. On the other, we have a sophisticated tooling architecture built on AST analysis and automated refactoring tools like Go Fix Rewrite. The intersection of these domains allows the development environment to become truly context-aware. Our core thesis is that by understanding developer intent, we can tackle technical debt at scale. Go 1.26 represents more than just a version update. It is a commitment to a seamless intersection of expression and automation, ensuring that large-scale codebase evolution becomes a standard, manageable part of the developer workflow.
To truly understand how we process code, we must examine the engine behind it. In the past, modification was handled via text replacement, relying heavily on regex and string matching. This approach was inherently clunky and prone to syntax errors because it remained unaware of the surrounding code context. Today, we utilize the Go analysis framework, the same robust engine that powers GoPlus and GoVet. By manipulating the abstract syntax tree directly, we move beyond simple text and treat the code as a structured hierarchy. This shift ensures that refactoring is safe, context-aware, and strictly respects scope and type definitions, providing a far more reliable foundation for complex transformations.
Moving into our language upgrade discussion, we are focusing on a significant refinement coming in Go 1.26, the simplification of allocation using the new expression syntax. Historically, as shown on the left, obtaining a pointer to a primitive value required a two-step process of declaring a variable and then taking its address. This created unnecessary boiler code for a very common operation. With the release of Go 1.26, this friction is removed. We can now allocate and initialize a value in one concise step. By passing an expression directly to the new function, such as new42 or new Alice, the language handles the memory allocation and initialization simultaneously. This update results in cleaner, more readable code and continues the trend of streamlining the developer experience within the Go ecosystem. Let's examine what we refer to as the magic, intelligent inlining. This new analysis framework traces the definitions of custom helpers to understand our specific intent and automatically replaces them with native syntax. By utilizing AST analysis, the tool can identify a utility function like PTR and refactor it directly into a standard native equivalent. This leads to the instant removal of internal utility dependencies across monorepos, significantly simplifying the codebase and reducing long-term maintenance overhead. Modernizer 1 addresses loop variable capture by cleaning up concurrency patterns used prior to Go 1.22. In the legacy pattern, the loop variable was shared across all iterations, requiring developers to manually shadow it inside the loop to prevent data races. This user::user syntax was a necessary but repetitive idiom used to ensure each Go routine captured a local copy of the data. As shown in the Go 1.26 fix, this scoping is now handled natively by the compiler. Each iteration effectively receives its own instance of the variable, allowing us to remove the redundant shadowing and write cleaner, more intuitive concurrent code. In Modernizer 2, we address the risks associated with standard struct tags by moving from omit_empty to the more precise omit_0. The challenge with omit_empty is that it often ignores valid zero values, such as a literal zero, a false boolean, or empty structs, leading to fields being unintentionally dropped from our JSON output. This can cause significant issues in API responses, where those zero values represent meaningful data. In the risky example on the left, an error code of 0 would be omitted, which could be misinterpreted by the consuming service. By switching to omit 0, as shown in the safe example, we ensure strict zero-value matching. This tag only omits fields that are strictly matching the zero-value definition, providing a much safer and more predictable way to handle optional fields in our Go structs. In this third installment of our Modernizer series, we are focusing on performance and memory allocations, specifically regarding integer to string conversion. On the left, we see a common but inefficient pattern, using fmt.sprint to convert an integer ID to a string. While convenient, this approach is relatively slow and causes unnecessary heap allocations because it requires parsing a format string and utilizing reflection. To optimize this operation, we should transition to the method shown on the right. By using the strongcof.itoa function from the standard library, we achieve a much faster native conversion. This direct approach significantly reduces overhead and represents a best practice for building high-performance Go applications where frequent numeric conversions occur. In this section, we examine the transition from the legacy sort package to the modern slices package introduced in Go 1.21. Before the advent of generics, sorting a slice of structs typically required sort.slice, which utilized a comparison function based on indices. This approach often felt indirect and relied on closures to access the underlying data. With the adoption of the slices package, we now use slices.sortfunc. This method leverages generics to pass the actual elements, A and B, directly into the comparison function, significantly improving type safety and performance. Furthermore, by incorporating cmp.compare from the cmp package, we simplify the logic to return a standard integer result, making the code cleaner and more idiomatic for modern Go development.
Surgical precision is achieved through granular execution. Developers can enable or disable specific modernizers using flags, which ensures a highly controlled migration process. In this example, the -4var flag is used to enable loop variable cleanup. Simultaneously, by setting the -omit0 flag to false, we can explicitly disable JSON tag updates. This level of granularity allows for a predictable and incremental approach to code-based modernization. To understand the strategic value of this approach, we can look at three key areas: managing debt at scale, standardization, and long-term readability. Starting with debt at scale, the primary advantage is that large monorepos can migrate to newer, more ergonomic language features almost instantly. This eliminates the need for labor-intensive manual refactoring across thousands of files, allowing teams to evolve their codebase efficiently. Next, we have standardization. By utilizing these standard features, we significantly reduce the reliance on fragmented internal utility libraries and custom helper functions. This ensures that the codebase remains cohesive and follows a unified, predictable structure. Finally, we prioritize readability. By adhering to standard Go idioms, the code becomes universally accessible. Any Go developer joining the team can immediately understand and contribute to the project without having to learn proprietary internal patterns, ensuring long-term maintainability. A truly satisfying developer experience is the cornerstone of our latest advancements. With Go 1.26, we are reimagining the maintenance lifecycle, transforming what used to be a tedious chore into a seamless, automated evolution. Our goal is to empower you to write the code you want right now, while allowing our intelligent tooling to automatically update and refine the code you already had. This approach ensures your codebase remains modern and efficient without the traditional manual overhead.